Hello everyone, I'm Wenliang Yin, and I was a master student from the University of Tokyo. My supervisor is Associate Professor Kohei Nage. Today, my presentation title is Investigation of the Fracture Behavior of the FRP Strengthened Reinforced Concrete Beam by 3D RBSM. The use of fiber reinforced polymer FRP as external bonding is a popular method for the strengthening existing reinforced concrete structures, thanks to its efficiency and ease of installation. And however, design against virus debonding failure modes is a significant challenge of it. Although experiments have been conducted to investigate debonding behaviors, complex degradation conditions make FRP strengthening a case-by-case matter in practice. To evaluate different repair cases, a simulation tool can save time and money. And for numerical analysis, the finite element method FEM is widely used to simulate the behavior of reinforced concrete structures. While the FEM can show the development and the distribution of stress well, it has difficulties in simulating natural cracking behavior. Due to the high nonlinearity of the concrete combining with cracking and slipping, discrete models that can predict the crack propagation appropriately can be a better alternative to the conventional FEM simulation. And the rigid body spring model is a discrete model that can consider the heterogeneous property of concrete. The element can be idealized as a collection of rigid bodies interconnected by springs. And Dr. Jiang has developed a rational FRP to concrete interface model in 3D RBSM program. However, his model is for the single pull-out test in small size and local simple condition. To simulate the structural behavior of the beam, new models should be made. And my objective is that to develop a rational and precise numerical simulation model that can predict the fracture behavior of the FRP strengthened concrete beam and explore the local behavior. Firstly, I will introduce my model building. On the left is model details. By using well-known points, the concrete is meshed into randomly shaped elements in RBSM. It enables consideration of the heterogeneous property of concrete by incorporating the internal features. The normal and shear springs in the constitutive model for the element are shown on the right. These works are done by previous researchers. And when considering the shear springs for the interface, the constitutive model is not like the typical bound slip model, because the typical bound slip model is a macro-scale model, and the interface is used to refer to the interfacial part of the FRP to concrete bond joint, including the adhesive and the thin layer of the adjacent concrete, instead of any physical interface in the joint. The descending branch in the curve includes the effect of the micro cracking in concrete. And for the interface model in our mesoscale simulation, concrete cracking is modeled directly. So the simple elastic plastic model is used for the shear spring of interface in our model. Then to my model setting, the geometry of the numerical model is based on the experiment conducted by one and shown in the slide. There are two kinds of simulation model were made: a reinforced concrete beam without and with FRP strengthening. And this is the model for the FRP strengthened concrete beam. And the springs at the interface between FRP and concrete should be modeled carefully for accurate simulation. In reality, a thin layer of the adhesive exists between FRP and concrete. The performance of the adhesive layer can be reflected in the interfacial springs between FRP and concrete elements. Considering the different failure modes, if both FRP and the concrete are assumed to be rigid bodies, the interfacial tensile strength is the force that can lead to interfacial failure, not the rupture tensile strength or of the interfacial adhesive material. And Dr. Jiang has done the parameter study of the relationship between the interfacial tensile strength F interface and the concrete surface tensile strength FST in his work. According to his result, to investigate the different failure modes, 3 different F interface values were selected to do the parameter study in this work. And then for the result and discussion, for our reinforced concrete model, the simulation results are in high agreement with the experiment. We can see the similar trend and the ultimate bearing capacity in the load displacement curve. and also the cracks. Then for the FRP strengthened beams, in the load displacement curve, the yellow, orange, and the blue line are of the simulation with different F interface values. And the red dot line is of the FRP bounded experimental specimen. Compared with the experimental result of the unstrengthened beam in black dot line, FRP strengthened beam have a certain increase in ultimate bearing capacity. And the same phenomenon happens in the simulation. And in the experimental result, once the FRP undergoes the complete debounding, the load capacity of the FRP strengthened beam decreases instantly. However, in the simulation result, the load capacity decrease caused by the debounding is not an instant process. After checking the debounding process and the strain distribution, this difference has little influence to our result before fully debounding happens. And then the crack geometry. The movie showed that the crack geometry of the experimental result and the simulation. In the simulation, debounding of the beam with different F interface values start at a similar position and then extend to one end. This intermediate crack-induced debounding failure is the same with the experiment. And when F interface equal to 0.5 times FSD, debounding occurs at the interface between FRP and concrete elements. FRP plate slips with the surface concrete barely detaching. When F interface equal to 2 times FST, mainly the surface concrete elements and the FRP are sport together. And F interface equal to FST is in between, with both interfacial debounding and the surface concrete spalling occurring. And then the stress and strain distribution. The debounding process for the case F interface equal to FST is summarized again on the left. We can simulate this phenomenon, this debounding failure in our model, as well as the internal stress condition shown in the movie on the right. Not only the debounding process, but the strain level is also agree with the experiment, according to the strain distribution of the FRP in different loading level. Black line is the experimental result, and the orange line is for the simulation. They agree very well before fully debounding. And then the local relative displacement. The advantage of our discrete analysis is that we can simulate the crack opening and the vertical displacement together. Two adjacent concrete and FRP elements are selected every 50 millimeters from the midspan towards the fully debounded side to investigate the local displacement behavior. And the graph shows the vertical relative displacement of the adjacent elements of concrete and FRP respectively. The horizontal axis represents the loading process. It can be found that there is almost no vertical relative displacement of the adjacent element at the midspan. And vertical displacement increased largely in concrete after debounding near 150 millimeters from the midspan. It means that shear sliding locally happened here. However, little growth in FRP after debounding in the same place showed that there must be a gap between FRP and the concrete. That means peeling can happen in the interface between FRP and concrete. The local behavior in the beam is not the same as the simple pull-off test. Our RBS model can directly model this phenomenon. This is our advantage. The result of the successfully simulating the local behavior, the microscopic behavior of the beam can be simulated. From the crack pattern and the local vertical relative displacement curve, our RBS model can successfully catch the mixed mode failure. And this is my conclusion. The simulation results are in good agreement with the result of tested specimen, and the interfacial tensile strength between FRP and concrete crucial to the debounding behavior of the FRP strengthened beam. And it can be seen that our 3D RBS model can simulate the complex behavior caused by local cracking behavior very well, which is hard for FEM models. Thank you very much.
Thank you so much, Wenliang. Now we have time for some questions. If anyone has one. Marcelo, please.
Yes, hello, thank you for your presentation, that's very good. I just would like to know if you had a chance to compare your results with code results like ECI code to see how conservative they are. Well, that's it basically.
Sorry, I didn't get what he asked.
if you compared the results that you had on your simulations with the results, well, the flexure capacity of beams that are on ACI code, for example, or in a specific code.
Yeah, I used the ACI code. The strength.
Okay, but did you compare I mean, the flexure capacity on
Flexure
your
capacity? Yeah, it's based on the experiment. It's based on the experiment done by Dr. Wan. You mean the capacity of the beam calculated by the ACI? Yes, it's near the capacity. It also the experiment is similar.
I see.
Marcelo, let me follow up. Can you calculate the flexure capacity for this kind of materials with FRP sheets by using conventional design code? He's working on a bit special type of specimen. I'm not sure if you can calculate the design values for this.
Design value.
No. I'm asking Marcelo.
Oh.
I'm asking Marcelo. He's working on design codes. He's a practical engineer. He often uses like ACI code or other types of design code to calculate the capacity of reinforced.
Yeah, if you compare the failure, well, when the failure happened with this model to the model using ACI code, I think.
You wanna know how conservative the design code is, right?
Yeah.
But his specimen has FRP sheets on the bottom of the specimen.
Yeah,
I'm not sure if you can
if you
calculate the capacity of such beam by using ACI code or something. Yeah. If he conduct experiments on just regular RC without any, FRP sheet or something.
Yes, the regular RC. Yes, I have one model compare model for the RC beam. Yeah,
without any sheet?
Yeah, without any sheet.
Okay. Without any sheet. I see some I see some sheet. But anyway. Okay.
Yeah.
Well, anyway,
I have the beam without FRP and with FRP.
Okay. Then
I also calculate the flexure capacity by the
design code.
Design code, so it's similar, also similar. We also the experiment and the simulation result, they are similar to the result calculated by the code.
All right, thank you.
Okay, thank you. Is there any other question? So maybe, okay, Motohiro.
Sorry.
No problem.
Thank you very much, Wenliang. If I remember correctly, you did some like parametric study to calibrate your models, right?
The parameter studies different
to calibrate your models, right? Model parameters, I would say.
Yeah.
To determine the numbers of actual parameters, you did some sensitivity analysis, parametric study, right?
And
what kind of calibration you actually did? What kind of data you use for validation? How did you decide the parameter numbers?
Actually, Dr. Zhang have done some parameter studies about the simple pool of test and about the shear springs, the parameter studies. And we can say that if F interface smaller than the tensile strength of the concrete surface concrete tensile strength, adhesive interfacial failure happens. And if it's bigger than 2 times the FST, the concrete would peel off.
So if you change parameter values, the
Yes,
simulation results, of course, will change.
yes.
And what kind of results you used to determine the parameters? You use the macroscopic strengths, for example, or crack patterns, or any other results?
Yeah, if we based on the experimental result, we can find that actually it varies between the FRP to concrete, and sometimes it actually in the experiment, mainly the surface concrete was peeled off, but so the surface of the concrete, we can see that the thin layer of concrete was peeled off actually in the pull-out test, and in the experiment that also happens.
Okay.
So based on the experimental result, we choose the but it's based on the working the workers, and maybe if the bond is not well when they they use the FRP. So in the actual condition, it's different.
Okay, thank you.
So I based on this experiment. So I use F interface equal to FST. So that two kinds of debonding happens. It had the concrete peeling off and the FRP detached.
Okay, thank you.